Okay. Hello, everybody. Welcome to our third TIES Fall webinar series. Today we have Dr. Abhirup Datta and Dr. Yushu will be introducing him. Dr. Yushu, please, the floor is yours.
Okay, yeah, thank you, Jeff. So today we will have the Dr. Data from the John Hopkins University to give us a presentation. So Dr. Data is an associate professor in the Department of Biostatistics at the John Hopkins University. So he completed his PhD in the biostatistics from the University of Minnesota. And Dr. Data's research focused on developing the methods on the geospatial data and the multi-source data with application in environment and global health. And his work on the nearest neighbors Gaussian process has become one of the most widely used methods for scalable analysis of the massive geospatial data. And his recent work focused on developing the theory and the methodology for combining the machine learning algorithms with traditional spatial modeling and application to the methodology to the air pollution and the infectious disease modeling and so on. And his research as a principal investigator is funded by the NSF and the NIEHS and the Bill and Melinda Gates Foundation. So he has received the Early Career Investigator Award from American Statistical Association section of the Environmental Health, the Young Statistical Scientist Award by the International India Statistical Association, and the Abel Ella Sharawi Earlier Investigator Award from the International Environment Society tiers. So, floor is yours, Dr. Data.
Thank you, Yuju, for the introduction, and thanks to Yulia for inviting me, and also to Jaidev. So, can everyone see my screen, and can you see my cursor?
Yes, yes.
Okay, great. Just want to say a little bit, because I have never given this talk before. I've given part of this talk and expanded on this many times, but this is more of a collage of different experiences I had working with machine learning for geospatial analysis. I come from a more of a traditional statistical modeling background, and have been predominantly using geospatial models for analysis of environmental data. But in recent years, there has been like increasing use of machine learning methods for similar problems. And I naturally got curious and have been trying to use these methods in many of my projects and compare how they fare with respect to the usual statistical models. And so this talk is basically a summary of different projects where I tried machine learning, and some where it worked better than the statistical models, and also some where it did not. And I'll try to explain why it did not, and where we can possibly combine ideas of both worlds to create new methods. So I'll go over 4 different projects here. The first 2 are more of success stories of machine learning that I've been involved in, and then and those the specific examples are trying to answer the question: did the COVID-19 lockdowns impact air quality, or coming up with better prediction models for air quality data using data from low-cost sensor networks? Then I'll also talk about certain projects where we tried to do machine learning and didn't work well. And one of the main reasons it didn't work well is that environmental data is often spatiotemporally correlated. And unlike statistical models where you can explicitly specify covariances between data points, that is not standard in machine learning algorithms. And you can do it in other ways, but they may or may not fare well. So in light of that, the last part of this talk will focus on development of new statistical methods from our team that sort of combines machine learning, but keeps the statistical framework of directly able to model covariances in the data. So the 4 different projects. Let's see how much time permits to kind of go over each of them. So the multiple projects, so there's work with many people. I've just listed some of the main collaborators here. The top row are students that have been fortunate to work with because they have led most of the papers. Orko was my former PhD student. He is currently a postdoc at University of Washington. Claire and Ventao are my current PhD students. And then in terms of collaborators, Kirsten is in environmental health, and Roger used to be in our department, now he's at UT Austin. And then Shimonto is at Cornell University, and they've worked with me on different projects. So the first story I want to tell is this project that we started.
Related.
Yeah, the project we started back in 2020 is that, like, did the COVID-19 lockdowns really change air quality? And we didn't really publish at that time. We did some analysis, and then within few months, hundreds of papers got published. In fact, there is this 2021 review paper that kind of summarizes over 200 papers on this topic. So it's a very widely discussed and published topic. And we went through many of these papers, and they use a variety of methods. Among the ones that do a formal statistical analysis, they use like mean differences, difference in differences, and also regression models. And then we kind of went over them, and we saw that there were some things that were not done in an ideal way, in the sense that some were not really like they were giving some estimate of this as an answer to this question, but that was not really answering the causal nature of the question, is that how much of the change that we saw can be really attributed to the lockdowns. Many of the methods did not account for meteorology, also many of them did. The one that kind of we saw feature most prominently was that almost none of the methods kind of tried what they did for 2020 on some of the baseline years to see if their method was giving any false positives. Because if your method is giving an impact of lockdown in 2019 or 2018, that's probably not the best method to apply in 2020, because there was no lockdown in those baseline years. So most of these papers did not do sort of validation using any sort of control group or baseline group. So Claire, who led this work really and came up with this idea of kind of framing the issue as a causal effect estimation problem. So basically, if we denote the pollutant concentration at time t as y of t, and lockdown is the intervention, and with a equals to 1 being that the lockdown was in effect, and a equals to 0 meaning that the lockdown was not in effect at time t, then we can write down two potential outcomes. So ya of t is the potential outcome at time t, such that the lockdown indicator is a, and that a can be 0 or 1. If it's 0, it means that we are looking at the potential outcome had there been no lockdown. And if it's 1, we are looking at the potential outcome if there was a lockdown at that time. And so the causal effect of the lockdown will be given by the average treatment on the treated. This is different from the average treatment effect, which is the ATE. This is the ATT, the average treatment on the treated, because we want to see during those months of lockdown, which was usually March of 2020 onwards for the cities that we studied, if there had been no lockdown, what would have been the air pollution? And then we take the difference and then we average it out. We don't want to do this for other months like January or February, which was previous to the lockdown. So this is causal effect, but on the treated population, and by treated with it just means that the lockdown indicator is 1, which are the months of 2020 after the lockdown was imposed. So typically mid-March onward. So that's why the quantity of interest here will be the ATT and not the ATE. Okay, so again, this is all clear. So she came up with this comparative interruptive time series idea that gives a very general framework to kind of come up with an effect size estimate for this problem. So you simply model your potential outcomes, YA of t, as a function of time, the lockdown indicator, and other covariates. These covariates will typically include all these meteorological covariates that are relevant, as well as seasonal covariates that account for like annual seasonality of air pollution. And then once you model this using the data that you have, which is both data after the lockdown, but also baseline data from before the lockdown, from both 2020 and previous years, you get an estimate of F, which is F hat. And then during those lockdown days, you predict both the counterfactuals, take their difference, and just take the average of those differences. So this would be the average treatment effect on the treated population, or the ATT estimate. So then we kind of went back and looked at what all the other papers were doing, and we realized that many of those methods that were being adopted can be framed as a SITS model, but with a very specific form of this outcome regression. So one of the methods that have been used is just looking at the difference in mean concentrations between pre-lockdown and post-lockdown to see if there has been a difference in the concentrations in 2020. This is we were able to show that this is exactly equivalent to a SITS model with this very simple outcome regression, having only the lockdown indicator as a covariate, and training this on data only from 2020. So you have data from 2020 both before and after the lockdown. You just fit this model, and then your ATT estimate. So this quantity in the previous slide, it exactly becomes this beta 1 hat. So this has been done commonly in some of the studies that were assessing the impact of COVID lockdown. So this is exactly equivalent to assuming this model, which basically ignores any sort of meteorological or seasonal changes in the year, as they don't feature in your outcome regression. Another mean difference approach that has been used is difference in mean concentrations for the post-lockdown period between 2020 and past years, or baseline years, so we call it DIB. This is also equivalent to a SITS model with the exact same outcome regression, but with a different training data set. So instead of the previous mean difference that trained on just data from 2020, both before and after the lockdown, this practice is equivalent to training on just data from after the lockdown, but for both 2020 and baseline years. And if you do that and you get your estimate of beta hat, this is exactly equivalent to the ATT estimate from a SETS that assumes this model. So this is better than the previous approach in the sense that it's comparing between the 2020 and the baseline years for the same time period. So it at least accounts for meteorology in some sense, but it kind of assumes that the meteorological trends that were there in the baseline years post-lockdown are exactly the same trends that we saw in 2020 during the same period, which is, of course, not fully accurate. Then you can do difference in differences, which is difference in means post-lockdown between 2020 and the baseline years, and take the difference in means pre-lockdown between 2020 and the baseline years, and you subtract the two. This also, we were able to show that this also becomes a SITS model with a lockdown indicator, a year indicator for the lockdown year, and the time indicator for the time to be past the lockdown date. And if you fit SITS using this model and take the ATT estimate of the beta 1, you will basically get the difference in difference estimate. So the DID has the weakest set of assumptions, so it's much better than the previous two. It only assumes that the within year changes in meteorological trends are similar across years. So this is still an assumption that we don't really need to impose, as I will show next, but it's a weaker assumption than the other methods. And there were also papers that used formal regression models. So linear regression being the most common. So you just model the potential outcome using the lockdown indicator and all your meteorological covariates as well as splines of time to model the seasonality. And then you get your ATT estimate as the beta 1 hat, which again, it becomes identical to the SITS ATT estimate under this outcome regression model. This is much more general, but its limitation is it assumes linearity in relationships. And so these were primarily what was done in the literature. So we added a new category, which is similar to what the linear regression was doing, but instead of doing it in a linear way, we'll just model a nonlinear regression. So F is now any nonlinear regression that can be a machine learning method or can be a GAM or something. We used gradient boosting and random forests to fit the data. So the post-lockdown data in 2020 informs the Y1T, and then pre-lockdown data in 2020 and all data in the baseline years informs the Y0T. So there's, of course, more data informing the Y0T than the Y1T, as we have much less data from lockdowns. This does not make any assumptions about linearity, and then once we fit the F, we can just estimate the ATT using this. Okay, so we first looked at the data. So we analyzed nitrogen dioxide concentrations from 5 cities in the US, in the northeastern US, Boston, New York, Philly, Baltimore, and DC. We used data from 2020 and 5 to 7 previous years, depending on how much data was available at each of the sites. So you can see these are the time series for 2020. The vertical line is the lockdown indicator for that city. So it was mostly around early March or mid-March for each of the cities, roughly around similar times. And then the dashed orange line is the baseline concentration, average baseline concentration averaged over the previous years. So you do see that the levels are lower in 2020 compared to the average baseline, but this is an unadjusted comparison. We would need to adjust for the meteorology, which might have varied between the baseline years and 2020, and it certainly does have an impact on air pollution. So we applied this method on 2020, but we also applied this method on each of the baseline years to see what effect a method would give if it was applied to, say, 2019 or 2018. And we did this for each of the methods that we considered. And this is where the machine learning methods really shone and sort of outperform most of the mean differences and linear models. It was basically that did not produce any sort of large effect estimate in the baseline years, which is good because there is no effect of lockdown in baseline years, as there was no lockdown in those years. Whereas if we look at the mean difference methods and the linear models, they produce very, very large and varying effect sizes for various baseline years. The DID, I think, among these methods was the best, but it still produced some large effects in baseline years. For 2020, most of these methods predicted negative ATT, which means there is a decrease in air quality. There's a decrease in air pollutant concentrations due to lockdown, but it's very hard to trust the linear methods or the difference methods, given that it also produces negative effects or just large effects in general in the baseline years, which was not the case for either of gradient boosting and random forest. They produced a negative effect for 2020 and did not produce any large effect in the baseline years. And then we looked at the percent differences in NO2 concentrations predicted by the machine learning methods and compared it to what was in published literature. And they kind of tally up pretty well. We saw roughly around somewhere between 20% or 30% difference for Boston and DC. We didn't see much difference predicted for Philadelphia, and this was in line with what has been published. There has been some effect size estimates that were negative, but often the confidence intervals in those published estimates covered 0. So this was kind of in line with that. And then we had lesser, but still negative effects for both New York City and Baltimore. So out of the 5 cities, 4 of the cities, we did see a decrease in air pollution concentrations as an effect of the lockdown using our comparative interrupted time series framework. So summary of this story, impact of lockdowns or other sharp interventions like a factory closing down. There have been such studies in Utah previously. Effect of such sharp interventions on air pollutant concentrations can be studied as a causal effect estimation problem using the comparative interrupted time series framework. And we kind of saw that most of the popular methods that were used are actually can be framed within this framework and correspond to very simplified models and assumptions that are probably wrong. And perhaps due to this reason, we see them predicting many false and large additive values in baseline years. The machine learning models are more flexible, and in this case, they were definitely a success story in the sense that they guarded against false effects in baseline years and still identified negative effects in 2020 for most cities. But it's not guaranteed that they will work well in any other application. And so the main takeaway for us was that if you're trying to do this kind of a study, you should definitely identify a control group or baseline group and apply your method there and see if your model or method is predicting false effects in that group. So the study really highlighted the importance of adequate validation using control data. So this paper is currently under revision, just the group of authors who were involved in this. Okay, the second story, and it kind of follows into the third story, is about predicting low-cost air pollution, predicting air pollution data using low-cost sensors. So the regulatory air pollution monitors are typically very expensive, and hence often the regulatory network is geographically sparse. For example, if you look at Baltimore, the blue and the purple dots are where there is a reference monitor measuring PM 2.5. So with two sites, and really this site is far out in the east, not in the city proper. So we really have one regulatory site in the whole city, and so we don't get any sort of information about the variation of air pollution concentrations within the city. And so there is now a low-cost network operated by the Search Center that has more than 40 multi-pollutant monitors in the city. So they're giving us data on air pollutants at much denser spatial resolution, but it comes at a cost because these low-cost sensors are much cheaper, but they're also less accurate than the reference monitors. So the data from the low-cost sensors need to be properly calibrated before being used in any study. So we had previously put forward a calibration model for the low-cost data. So basically these sites that you see, the blue and the purple ones, there is both a reference monitor as well as a low-cost monitor put in there. This is because we want to kind of use the co-located time series to understand the biases in the low-cost data and come up with the statistical calibration equation that we will apply to all the monitors elsewhere. So this was a very simple model. We have YT as the low-cost sensor PM 2.5 data at time t. XT is the reference PM 2.5 data at time t. We only have this as in one or two of the sites. This is what we want to predict at other locations. And ZT are the other covariates, which are typically temperature, relative humidity, as well as some daily and weekly periodic terms. And we had a very simple regression model regressing the reference PM data on the low-cost data and the other covariates. There's a reason I write XT on the left-hand side and YT on the right-hand side. I'll explain it. It's not really conventional to write the dependent variable as X. But anyway, I'll come back to that later. But the model was very simple. In those co-located sites, we had both the reference data and the low-cost data and these other covariates, so we could train the regression model. get estimates of these betas, and then apply this to the low-cost data at other locations and get estimates of XT, or the reference PM2.5 at those locations. So we compared this regression model to the raw data, as well as just a calibration equation that was based on simply laboratory experiments. So you can see the raw data is like very, it over predicts a lot, and then the RHT correction does quite a bit well, but they still tend to kind of be quite poor compared to what the reference measurement is. So MD is the Maryland Department of Energy, and so there was definitely a need for calibration in this case. So after we applied the model, we got much improved results, and we published this linear regression paper. But then we had a postdoc, Andrew Patton, who said that, okay, the linear regression seems to be doing well, but what about trying some machine learning methods? And so we looked at the calibration performances between linear regression and the machine learning methods. And it was really the case that he used a version of boosting. It was really that the boosting was doing better, especially in terms of identifying some of the peaks, than the linear regression. And it kind of led to a reduction of RMSE by around 10 to 20%, depending on the season. So after we had the linear regression paper, we also had this boosting paper, and we worked on that. So again, this was a case where the linear regression did a great job in kind of removing biases to a certain extent, but because of the linearity assumption, it is slightly restricted. And so the boosting with abundant data did a better job and had better RMSE and better predictions in general for prediction of the reference PM levels using the low-cost sensor data. So these are two papers here. This was the linear regression model, and this was the boosting model. So again, this was a success story of machine learning method, given that the linear regression, it provided a clear improvement over the linear regression, and so there was a value in modeling things in a nonlinear way. So continuing on this example, this will highlight one of the downsides of the machine learning method. So one thing we noticed is both the linear regression and even the boosting, but to a lesser extent, tended to underpredict high air pollution peaks. So an example here, this is the Maryland Department of Energy reference data, and this is the predictions from the regression calibration using just the low-cost data. So you can see that overall the prediction is doing fine, but then there was this big peak in December 23, and it was severely underestimated. And we saw it was not that peaks were very common until last summer, but whenever there was a peak, we saw this to be a common occurrence, that the regression-based calibration would tend to underestimate the peak. So in general, we looked at data points and classified them into the good air quality index and moderate unhealthy air quality index. If the true index was good, then the predicted index was also good 96% of times, which is great. But if the true index was moderate unhealthy, then the correct classification went down to 77%. So often moderate data points were classified as good, and unhealthy data points, which were very rare, was classified as moderate. So we saw this phenomena that the regression calibration that we had published previously does well overall, but it would tend to underestimate the higher pollution peaks. So this is another paper also led by Claire. So Claire looked into this regression calibration model that had the XT on the left-hand side, which are the reference PM2.5 levels. The YT is the low-cost sensor PM2.5 levels, and the ZT are the covariates. And she basically kind of came to the conclusion, both theoretically and through empirical studies, that if you fit this model and you take the residuals from this regression model, these residuals are negatively correlated with the true pollutant levels. What this means is that as the true pollutant levels are high positive, these residuals become high negative, which means that the predictions are underestimating. And we were able to show this theoretically for this linear regression problem, but we also saw this when plotting the residuals from the regression calibration as a function of the true pollutant level. So, and this is just a property of linear regression. It's nothing nothing radically new, but it's just this is not what we want when we're trying to predict air pollution concentrations, because in a way these high concentrations are what we care about the most because they affect health disproportionately. The second problem is that when we apply this calibration, so we train it at this co-located site where we have both reference data and the low-cost data. We train it, we get the estimates of the regression coefficients, and then we apply this regression coefficient or this calibration equation at all of these other low-cost sites to get the estimates of the true concentrations. So this ignores the fact that the true pollutant levels are spatially correlated, because we are simply applying the trained calibration equation separately at each site. So it ignores spatial correlation. And also this training for estimating the regression model coefficients is done for just one single window. We are not using the reference data available at this site or this site when we are predicting in the future. So we are simply applying the calibration equation to the new data for every low-cost sensor individually, ignoring the fact that for that same time point, we also have a reference data available here and here, which can potentially be used in the model because levels are spatiotemporally correlated and improve the calibration. So to do this, the first thing we did was flip the roles of X and Y, and which is why in the previous model, I wrote X as on the left-hand side and Y on the right-hand side. Was once we correct it, Y goes on the left-hand side, X goes as a independent variable in the regression. So we basically inverted the regression model. And in many ways, this is a more natural model because we are modeling the low-cost data as a noisy and biased version of the true pollutant level. So this is a much more generative model that's reflective of the actual mechanisms. And we were able to show that if you fit the inverse model, get the residuals X hat, because even if you fit the inverse model, you're still predicting X hat, not Y hat, because you get the low-cost data Y hat. If you predict X hat, the residuals from this inverse model are uncorrelated with the true pollutant level. So we will not, we don't expect to see these underestimations at high levels of XT because residuals are going to be roughly uncorrelated with XT. Another advantage of this inverse model is that now that Y is on the left-hand side, X is on the right-hand side, we can put together a second stage spatial model for X because we know that true pollutant levels are correlated across space. So what we do is for a given time window using the co-located data, we train the observation model and we get the estimates of these regression coefficients. So this becomes our, now when predicting our air pollution concentrations at a new time point, these coefficients are now known because they're coming from the trained observation model. Y is also known, so the unknown quantity here is now X that we want to infer upon. So this becomes our observation model, and then we have a second stage state space model for X, which is simply a conditional Gaussian process model conditioning on the available information on the true pollutant level at this reference location S0, which in our case was the blue dot in the map. Because we will have information about the reference levels at the latest time point, we want to use this information. And so we have a joint model for both XST and XS0T, which is a Gaussian process. And then from that, we can easily derive the conditional Gaussian process model with the Kriging mean and the Kriging variances. So these two pieces are very similar to the two pieces in a Kalman filtering, except that in a Kalman filtering, the state space model is dictating evolution over time. Here, state space model is dictating evolution or sort of the structure of air pollutant concentrations across space. And then we have an observation model coming from the low-cost sensor data. So with these two pieces, we can do a Kalman filter type update if we want a frequentist solution to this. We can also do a Bayesian model where this is our first stage model, and this is the prior for this unknown quantities XST. So we can do either ways of implementation and then get better estimates of X, of the true pollutant levels X, that are both spatially informed and also informed by the observed reference concentrations at those collocated sites. So let's look at some of the performances of the regression calibration and filtering method. So it does much better in terms of the root mean squared error. But more importantly, if you look at predictions for that peak on December 23, black is the true value and red is the predicted value from the filtering method, whereas blue is the predicted value from the regression calibration. So the GP filter does well both when the levels are low as well as when the levels are high, because it doesn't suffer from the underestimation issue on account of using the inverse regression. And then we plotted maps for that day using both the GP filter and regression calibration. The squares are where we had reference data, and you can see the calibration agrees with the color we see for the reference data. Whereas when we do the regression calibration and calibrate each location separately without using spatial information and without using the data that's there at these reference sites, the underestimation is very clear for most of the locations. So this was great. We published this paper, but then the next natural question that we thought Claire will address in her thesis was an extension for nonlinear observation model, because the relationship between the low-cost sensor data and the true concentrations can be nonlinear as a function of covariates, especially with relative humidity. So we thought, okay, instead of a linear regression, why don't we fit a nonlinear model using some machine learning algorithm or a GAM and see if we can improve upon the linear regression thing. So the setup is exactly the same, just that we replace the linear regression with a nonlinear model here. We keep the conditional Gaussian process prior for the true pollutant concentrations, and we tried both neural networks and GAMs for this task. So we tried this during this summer where we had these very high peaks in Baltimore coming from the Canadian wildfires. And these are predictions at 3 low-cost network sites, and these are the true value at the nearest reference site. And the top row is the linear GP filter, and the bottom row is a nonlinear GP filter using a GAM for the observation model. As you can see, some of the predictions from the GAM are absurd. It's going into very high negative concentrations, where the linear model is doing pretty well. Any guesses why this is happening? Don't see anyone taking any guess. We were very perplexed as well as to why this is happening. Why would it may predict like absurd positive values, but why would it predict absurd negative values? So the issue is basically extrapolation in nonlinear models. So this is the training data that is used. Because we don't get high peaks most often, the training data, the concentrations in the training data is mostly within like 0 to 20 at best micrograms per meter cube, which is very much on the low end of things. And this is what the concentrations looked like during the peaks. It went as high as 250 micrograms per meter cube. There is nothing in the training data that informs how a nonlinear curve will extrapolate to these ranges. And the problem is exacerbated because we are doing an inverse regression. So just to kind of illustrate with this very crude drawing here, we get data, training data, for a very small range of x. And using that, if we fit a nonlinear model, so this is a cubic model, a nonlinear model, a cubic model may fit very well to this part of the training data, better maybe than a linear model, but it has no obligations to behave in a reasonable manner outside of the training data. Now we are probably looking at concentrations here, and we observe a low-cost data point, which is somewhere here. But because of the cubic shape, it's unlikely to choose a point here because the likelihood is minimizing, the negative log likelihood is minimizing this term. So if you look at somewhere here, the difference is very large, whereas if you look at somewhere in the negative side, the difference is much small. So there is, unless we explicitly make like a monotonic nonlinear function, just using like, and which is not the case in most of these machine learning methods, just using off-the-shelf approaches is not going to work because it's going to choose absurd ranges of values. So this was a big roadblock for us, and we figured out why it is doing badly. We haven't quite figured out what's the best way to rectify it. But it was clearly an issue where the linear model did great in this two-stage filtering approach, but the same idea, which we thought would be like the natural next step for the paper, did not work with nonlinear observation models. In general, machine learning methods, unless you put in explicit constraints on how the function will behave, can extrapolate very weirdly if you're going far away from your training data. And the problem is especially worse in inverse problems because like our GP filter setting, because of the issue I demonstrated graphically. This is the linear filtering paper. There's of course no paper for the nonlinear method because it did not work. So the final problem that I'll talk about, and this is usually the topic I have presented most, so I wanted to talk about the other three examples, is one major issue for machine learning algorithms in for environmental data is that environmental data typically has spatiotemporal correlation, and there is no explicit mechanism to input covariances among data points in most machine learning algorithms. So this is an example of a nonlinear mean function, a sine curve, which is the blue line. And this is what is being fed by a random forest when there is dependence in the data. As you can see, that the fit is just poor. The green line is a fit by random forest generalized least square, which is a new method we have come up with that kind of allows you to input spatial covariances in the random forest algorithm. And we'll talk about that next. But you can see the issue of ignoring spatial correlation or temporal correlation when estimating nonlinear mean functions by machine learning algorithms. So how do we modify machine learning algorithms to include spatial covariances? So a typical geospatial setup would have you would observe the response y, a set of covariates x at a location s. And the goals of the geospatial analysis would be to understand the relationship between x and y and to predict at a new location. And the sort of the staple geospatial model to do this is this generalized linear mixed effects model, which will model the response as a function of your covariates via linear fixed effect and a spatial random effect, typically modeled as a Gaussian process, and then linking this mixed effects model to your outcome by a suitable link function depending on the type of outcome you have. So if it's continuous outcome, then you're modeling using Gaussian errors, so the link is identity. If it's count outcome, then it's log link. If it's binary outcome, then it's probit or logit link. And the Gaussian processes is a very popular choice for modeling the spatial dependence, although splines and other basis function approaches can also be used. I'll mostly be talking about Gaussian processes here. So basically, if you observe data at n locations, the random effects at those n locations can be stacked up as a multivariate Gaussian distribution whose ijth element gives you the covariance between the ith location and the jth location. And that specification of this covariance function kind of encodes ideas like stationarity or isotropy, in the sense that things that are closer to each other are going to be more highly correlated. So I really like this generalized linear mixed models. I think it has the interpretability that you can directly understand the effect of the covariates X on the outcomes Y through this regression coefficients beta. It separates out the fixed effects and the random effect. The Gaussian process is flexible enough to model complex structures, complex spatial dependent structures, but yet it requires typically 2 or 3 parameters to specify it, unless you have a very non-stationary problem. It also allows predictions at new locations via Kriging, which are simply conditional normal distributions. So it's very convenient. So I really like this model. It's kind of my go-to for any geospatial analysis. The only downside of this is the strong assumption of linearity of the fixed effect. And that's where you see many of these machine learning methods performing well, as I showed a few examples today, because they relax this linearity assumption. And especially if you have more data, you would be tempted to try out a nonlinear model just to see if you get better predictive power. So our idea is very simple. We will keep everything same about this generalized linear mixed model, except that we will change this x transpose beta part and replace it with a nonlinear function m of x. And we will model m of x using a machine learning model. Everything else is same. It retains all the advantages of Gaussian processes. It keeps the additivity of the fixed effect and the spatial effect, and it can do predictions via Kriging. The tricky part is how to estimate M using machine learning in presence of the random effect covariance. And the answer to this depends on what machine learning algorithm you use. So there has been some work here. So we have done extensions of random forest to model spatial covariances for continuous data and for binary data. Fabio Sigrist has done this, has used a very similar idea for gradient boosting. And then we have recently extended neural networks to account for covariances. So I'm running out of time, so I'll just give the main idea and then not go over the details, and I'll point to the papers so that we leave some time for discussion. So if we go back to the linear mixed effect model, we can marginalize out the random effect and these error terms to have this joint errors that combines the spatial random effect and the noise, and its variance will be the spatial variance plus the noise variance. And we can write down this hierarchical model equivalently as this marginal model with mean x beta coming from the fixed effect and the covariance sigma coming from the Gaussian process and the noise variance. And if sigma was known, then the maximum likelihood estimate for beta becomes this generalized least square estimate, which is something we're very familiar with, which is simply minimizing this quadratic form, and this will have a closed form solution. So we know how to incorporate covariances if the mean function is linear. Now we want to do the same thing when the mean function is nonlinear, but everything else is same, like sigma is the same Gaussian process matrix. Ideally, what we want to do is basically minimize over a class of nonlinear functions this same GLS loss, given the covariance matrix sigma. So this would allow you to explicitly encode the spatial covariance or temporal covariance if you have time series data into the covariance structure while you are estimating the parameters of your nonlinear machine learning model. The implementation will depend on the machine learning method. I have a lot of slides on that, but I will just skip it and maybe. So for random forest, basically, you can see that it's the loss function it uses, it essentially becomes a least square loss with a binary design matrix. So once it becomes a least square loss, you just change it to the generalized least square loss with the spatial covariance matrix. And then the random forest estimate becomes a generalized least square estimator. For neural network is a very specific family of covariances. We also do the same thing, but I will skip the details. I'll point you to the papers, but I'll just show some examples. This is a non-spatial neural network versus the GLS neural network, and we compared them for the estimation of the mean, and as you can see, it clearly does well. And then there are other ways of incorporating spatial information into neural networks, namely, like you can add additional splines as additional covariates, or you can just input the latitude, longitude. Generally, using the GLS approach, where you can explicitly incorporate the covariances and not just splines or latitude, longitude, tends to do better, or at least equally to these methods. And we did this across a vast range of simulations, and the results hold out. Also, we did some of the first theoretical guarantees for this approaches. We were able to show that if your data is coming from a dependent process, like a spatial Gaussian process or an autoregressive time series, if you use this random forest GLS or the neural network GLS methods, they're going to give you consistent estimates. So some of the examples where consistency holds include the spatial matter and Gaussian process, as well as autoregressive time series. So I'll skip to discussion. The off-the-shelf machine learning methods cannot incorporate spatial covariances like the way we do in traditional spatial modeling. So we have modified random forest and neural networks to do the same by using GLS laws. The implementation of these are very different, but I didn't get a chance to talk about that. But the random forest paper is published, and there is a R package called random forest GLS where you can use it for both spatial data and autoregressive time series data. The neural networks paper is under revision, and this is the archive link for it. Okay, with that, I'll end so that we get some time for questions. Thank you.
Thank you so much, Dr. Abhirup Datta. That was such a nice talk. It was very insightful, and I would ask all the participants to unmute and give Dr. Datta a round of applause. And with that, we'll take questions from the audience. You can feel free to type if you have any questions, or unmute and ask. And I guess I can begin with one question. So, Dr. Datta, what about, have you considered high dimensional data within your models, and how machine learning and general all the general statistical learning methods perform when you have very high dimensional data like the SST and sea surface temperature data, etc.?
Very good question, Jaidev. So it really depends on what we mean by high dimensional data. So there are a few different meanings. So one is we have a high dimensional set of covariates at every location, which is like the standard high dimensional regression setup. I have not dabbled too much in that, partly because I have not faced applications where that is the situation. But there are a lot of methods that kind of do like a lasso type of regression in the spatial setup. So you have this GLS loss, then you add a lasso penalty. So there is a paper by Nandi and Maiti in GRSSB. So they call it GAM GLS, which is, again, very overlapping with the idea of random forest GLS and neural networks GLS, but they do it in the context of GAM. And there they allow the covariates to be high dimensional. And then they use the GLS loss, but then with a lasso penalty to account for the high dimensionality. So that can certainly be a solution. There is also high dimensionality related to the number of locations. So if you have large number of locations, your covariance matrix becomes big, and inverting it becomes problematic. So there, I think we can, and for both the random forest and neural network, we use the nearest neighbor Gaussian process, and that helps with the scalability. So the random forest is still slow. I think it doesn't work well for more than, say, 10,000 locations. The neural network is much faster. It's scaling up easily to 500,000, which is part of the reason we also wanted to kind of have a neural network version of the method. So that sort of high dimensionality can be taken care of. Going back to the sea surface temperature thing, we, I think, recently did sort of an overview paper where we used sea surface temperature data and analyzed it with both machine learning and traditional spatial models. And I see Wesley here. Wesley was one of the leaders of the paper. It was interesting in the sense that we saw the linear models to do quite well and at par with the machine learning models. So another example where you don't necessarily need to kind of use machine learning if you can have a sufficiently rich statistical model. Yeah.
Thank you. Uh, Anybody else has questions, please feel free to unmute and ask Dr. Datta. Okay, so we have one in chat.
Yeah, I see the question that does taking the latitude longitude as inputs take into account the spatial variability of environmental data when using neural networks? It's a good question. I think it sort of goes back to this very old problem of whether you want to model spatial dependence through the mean or the covariance, because you can do it both ways. You can model it through the mean using polynomials of your latitude, longitude, or basis functions, or you can model it through the covariance using Gaussian processes. Both tends to work, at least in the case of linear models, fairly well. But at least for the machine learning models, just inputting latitude, longitude, and just hoping that the machine learning models will capture the nonlinearity because they are a class of nonlinear family, that doesn't seem to work well in practice. Maybe with like lots of data and with a very complex neural network architecture, it will work, but it's much simpler to just input it in the covariance using the Gaussian process. Whereas you'd probably need to kind of do a lot of curation of creating best basis functions, best choice of neural network architecture for it to work by directly inputting it.
Yeah,
Yeah,
okay.
I saw the question about spatiotemporal. So Chris Weichel has done a lot of work on spatiotemporal modeling using machine learning algorithms. I would recommend you to look up his work, and also he cites other people's work that are relevant. I personally have not done too much of spatiotemporal work. Uh, in principle, these methods can be extended to the spatiotemporal setting where your covariance matrix is not just going to be a spatial covariance, but will be a spatiotemporal covariance. So, like conceptually, the extension is you can see what the extension would be, but to actually implement it, because your data dimensionally increases quite a bit and sort of deal with the computational challenges, it will be definitely a follow-up work, but we haven't done it yet.
Did you have a question?
Oh yeah, actually I have similar questions. I mean about the spatial temporal forecasting. Since Dr. Data, you mentioned your recent paper, so that is the grounding networks with the generalized least squares. I'm just wondering, so can this approach can be applied to the involving networks or some dynamic networks? Yeah.
Yeah, so if it's just temporal, the random forest GLS software has it allows you to fit autoregressive time series, like data, like a nonlinear mean that has been modeled by a random forest with the covariance structure coming from autoregressive time series. So you can just use it, and would be happy to get some feedback on that. If it's just temporal, then we have that extension in the package, but we haven't done the spatiotemporal part specifically. Yeah.
Okay, thank you.
Yeah, and thanks, Wesley, for the review paper. Good to see you.
I have another question. So, Dr. Datta, what about graphical models within the framework for estimating of covariance, especially because the graphical models have a very nice causal, like when you take direct directed acyclic graphs, they have a very nice causal interpretation as well that comes sort of as a bonus with the estimation.
Very good point. I think the one of the requirements for graphical models to estimate the covariance matrices is that you would have some sort of replication in your data based on which you can estimate which edges will be zero and which will be non-zero. If we are working in sort of the stereotypical spatial setup, we just have one snapshot of the data, so there is no replication. But if there is replication, whether it's across time and we can kind of either model the time or ignore the time to some extent, then you can sort of be more non-parametric about your covariances. So you can choose to not use these covariance families, but use actually like estimate the covariances using graphical models. Yeah.
All right.
Hi, Professor.
Thank you.
Yeah, I have a question.
Yeah.
It's a basic question that sometimes when we see the spatial autocorrelation or temporal autocorrelation, but sometimes the linear model uh, might give the better prediction compared to spatial or temporal or spatial temporal. Then how do you deal with these things in your paper? That how do you explain such things? And you already know that there is spatial and temporal autocorrelation exist, but still prediction wise, simple linear model is giving better prediction. Then how to tackle these things?
That's a very interesting question. I don't remember seeing too many instances of cases where there was a strong spatial or temporal correlation, but a simple linear model ignoring that gives better results. I would probably still like try to understand why the spatial model is giving worse results. Maybe it's like using some assumption that is not true, like it's using like a stationarity, whereas there is like a large degree of non-stationarity before kind of just going with a linear model that ignores all the spatial temporal component. Probably, I think if the spatial temporal model is giving worse results, it may be
So,
related to some incorrect assumption in the spatiotemporal part of the model that we'll try to improve upon.
so better meaning it's like it is not giving better compared to linear. So
Right. Okay.
in case of like when we don't consider the observed location in test, so in that case, spatial is giving better, but the case where just unobserved time points, like for future time points, if I consider, and it gives almost similar results, not significantly better,
Right.
then I'm
Yeah.
just
So I
asking
think
that.
what we have seen is that if we are, say, predicting far away from the data locations, the
Yeah.
strength of the spatial part of the model goes decays, and so it's the prediction essentially comes from the linear model part of the model. So that is common. So if there is weak spatial signal, or you're predicting far away, far out into space or time, that can definitely happen. But if we're predicting somewhere close to where we have data, generally the spatial model, especially with kriging, it really does, it usually does quite well.
Thank you.